if you have a function that is a function in x as well as y, in other words, it's one-to-one, like this particular function is in this graph, where it passes both the vertical line test and the horizontal line test, then technically you can use either x or y as your variable of integration. It's kind of whichever one you want. And that's what this is saying up here. Sometimes it's simpler to solve it for x than for y, but you have to pay attention to what you're doing. I mean, that's only true if both are an option to you, but they are in this particular problem. So in this particular one, we're going to do this problem with y as our variable. Why? Well, because it's set up that way. I mean, it's set up as y as our variable, so why not use it? I mean, we see the function in y right here, and we see the domain, if you will, for y right there. So y is going from 1, which is right here, up to 10, which is right here. So that's the section of curve that I've drawn. All right, well then if we want the arc length is the integral from c to d of the square root of 1 plus, in this case it'd be h prime of y because h of y is our function, dy. So I'm going to show you in this example that it works even if you use y as your variable. It'll be fine. All right, well we're obviously going from 1, which is our starting point. Right, we start over here at y equals 1, and we end over here at y equals 10. And since we're integrating this back to y, it's only the y variables that matter. Excuse me, the y values that matter, 1 and 10. And then it'll be the square root of 1 plus, oh, we need to find the derivative. We need to find that derivative so that we can substitute it in. All right, so let's go find that derivative. So I'll just put it in over here. H of y was equal to 2/3 times y minus 1 to the 3/2. So h prime of y is 2/3 times 3/2 times y minus 1 to the 1/2, which would be just y minus 1 to the 1/2. Because of course 2/3 and 3/2 will divide and make 1. So that's gone. Okay, so then I will go put that into my formula. So I will say that I'm going to take y minus 1 to the 1/2 and I'm going to square it. Well, that's convenient for me because when you square something to the 1/2 power, it makes the power disappear, which is very nice. So this is the integral from 1 to 10 of the square root of 1 plus y minus 1. Which is even nicer because then the 1's disappear, because 1 take away 1 is nothing. So that would mean that we're taking the integral from 1 to 10 of the square root of y dy, which of course is the integral from 1 to 10 of y to the 1/2 dy. All right, well, the integral of 1 to the 1/2 is y to the 3/2 times 2/3. We're going to take that from 1 to 10, which is 2/3 times 10 to the 3/2 minus 1 to the 3/2. 10 to the 3/2 is 1,000 on the square root of 1,000. Because 10 to the 3rd is 1,000, and the square root of 1,000 is 10 square root of 10. So this is 2/3, 10 square root of 10 minus 1, because 1 to the 3/2 is 1. And that would be meters, because this is arc length. It's the single dimension. It's literally the length along that piece of curve, if I could stretch it and make it flat. That's not really very useful to us in terms of knowing the answer, so I'm going to go grab a decimal approximation just to give me a clue of what's going on here. And it tells us it's about 20.45, or 415, excuse me. So 20.415 meters. Well, that wasn't too bad. Even though it was with respect to y instead of respect to x, it worked out beautifully. But what if we tried to do the same problem in terms of x? Then what would happen to us? Now we can do it because, of course, this is also a function in x if we can just solve it. So h of y was equal to 2/3 times y minus 1 to the 3/2. That is x, right? Because it's a function in y. All right, well, I obviously want to get rid of the 2/3, so I'm going to get y minus 1 to the 3/2 equals 3/2 x. Multiply both sides by 3/2. And then I want to make the, well, here, let me show the work there. So 3/2 here, 3/2 here, no problem. My next step would be to try to make the 3/2 power disappear. So I'm going to raise both sides of the equation to the 2/3 power. So over here, 2/3 and 3/2 will multiply to 1. So I'm going to be left with y minus 1 equals, and then it's 3/2 x to the 2/3 power. So then what's y equal to? Y is equal to 3/2 x to the 2/3 plus 1. This is now your function in x. Okay, sure. All right, if that's my function in x, I know that for the sake of finding the arc length, I'm going to need the derivative. So the derivative of that would be f prime of x, which is equal to, oh boy, okay, so bring the 2/3 down. So 2/3, and then it'd be 3/2 x to the negative 1/3, because of course we subtract 1, multiplied by the derivative on the inside, which is 3/2. So a little chain rule. And then the derivative of 1 is 0, so that's gone. 2/3 times 3/2 disappears, and so that leaves me 3/2 x to the negative 1/3. Or if you like, that's 2/3, or 2/3x to the positive 1/3, right? Because of course we can take the negative power and make it reciprocal. This x is technically in the numerator, so when I reciprocate it, sure, it goes into the denominator, right? Either one of those is fine. Okay, so now let's find the arc length. The arc length would be equal to integral from something to something, I'll be back for that, the square root of 1 plus that 2/3 2/3x to the 1/3, or if you wanted to use the negative one, it doesn't make any difference. Both of them are pretty terrible, dx. And I'd be using x values of, let's see here, the start is over here, so the start is at x equals 0, and the end, when y was 10, is x is equal to 18. So I'd be taking the integral from 0 to 18. But we have a problem because that's going to be awful. This is not going to work out remotely nicely. This is just an awful, awful integral. So this is the integral from 0 to 18 of the square root of 1 plus 2/3x all to the 2/3 power. And there's no u substitution in the world that's going to help us with this. This is just atrocious. So and remember, u substitution is kind of all we have for advanced integration techniques. And u substitution will not work here because that's x in the denominator, just for starters, because that's x to the negative 1. It's going to be awful. I mean, if you tried to make u equal to 2/3x, that would be 2/3 x to the negative 1. The derivative of that is negative 2/3 x to the negative 2. We don't have it anywhere in the problem. Like, there's no, this is just awful. It's not going to work. So we would have to use Desmos. Let's go try it. So just to prove that this would work out. All right, so I have it right here that x is equal to 2/3 y minus 1/2 to the 3/2. And I have f of x is equal to right here, 3/2 x to the 2/3 plus 1, right? Okay, so according to me, these integrals should work out. So the integral from 0 to 18 of the square root of 1 plus f prime of x squared dx. So it is the same, but it's not something we would want to find by hand, right? It's too difficult an integral to do by hand. And that was my right here. There are often arc length problems that you can often do one way but not the other. Or if you can do both, sometimes one of them will be way easier than the other. So in this case, the y was way easier than the x. As a matter of fact, the x was not really kind of possible knowing what we know. So in our example, using y as our variable was easy. Using x was impossible to do by hand. Now, it's a reasonable question to ask, where are we going with this? Like, why do we spend so much time with arc length? And the answer is arc length leads to something else, because knowing what the length of an arc is along that curve can help us find something else. But you'll have to wait for 6.6 to find out what that is. I'll give you a hint. It's surface area. But we'll talk about that in the next batch of videos.